In this video, we're going to start looking at algebraic kinematics in one dimension. When we're talking about algebraic kinematics in one dimension, what are we talking about? Okay, so first of all, we're going to be doing all this stuff algebraically. So we're going to be solving problems in this module using algebra, but we're not going to be using any calculus. Okay? And when we talk about kinematics, we're talking about the study of motion without being concerned about its causes. So later on in this course, we're going to talk about forces and different things that can cause motion, but we're not interested in that right now. Right now, we're only interested in the motion itself. We're not concerned about the causes. And when we say one dimension, as we do here, in one dimension, oh, that doesn't highlight. There we go. In one dimension, we're talking about moving along a straight line. Okay, so we're only concerned about motion in a straight line. Okay, so we're going to need to start by defining a number of different variables. We're going to be talking about things like position, displacement, velocity, distance, acceleration, things like that. So in this first video, we're going to focus primarily on just defining all these things, and then in future videos, we're going to develop some ideas on how to solve problems with some of these ideas. Okay, so first of all, let's start off with position, displacement, distance, and distance traveled. So we probably all have a pretty good intuitive understanding of what these things might be, but it's better to have a little bit more of a sort of maybe a more rigorous definition to work with here. Okay, so for position, the position of an object is described with respect to some convenient reference frame, right? So we're going to be required to impose some sort of a coordinate system on whatever problem we're looking at. We're going to need some sort of origin of coordinates. Let's say, for example, we're talking about where a store is in relation to where we are now. We would need to say something like, well, where we are now, this is going to be the origin of the coordinate system we're talking about, and the store is 5 kilometers west or whatever, right? So we have a direction and we have a distance. So position works very much like this. Since we're working in one dimension here, our position will usually be either x or y, depending on which of the sort of traditional coordinates we want to work in. We're going to see more about that in a moment here, but let's move on to displacement. So displacement is defined as a change in the position of an object. So if x naught is our initial position, and we have some final position xf or x final, our object's final position minus its initial position is our displacement, and we can see that described here in this equation. And so note that this triangle here, this capital, well, this triangle is a capital letter delta in Greek. Okay, and in general, this capital Greek is widely used to indicate the change in some quantity. So what we're talking about here is the change in x, and the change in x is equal to our final position minus our initial position. Okay, and so that's the definition of our displacement. Distance is described just below, so we're going to be looking at distance here, and the distance is just the magnitude of the displacement. So when I say magnitude, in one dimension, we're just talking about the absolute value of. So we can have a displacement that's negative or positive, and that would point either down the right or the left of our x-axis. But our distance is just the absolute value of that. So we're only interested in how far this thing has traveled, right? So it's the absolute value of delta x. And again, note that this absolute value here indicates the magnitude of the quantity which we're looking at, and in one dimension, the magnitude and the absolute value are the same thing. We're going to see other examples as we move on in subsequent chapters. Okay, so that's three of our new variables that we're going to need to think about. Distance traveled is defined as the total distance traveled between 2 points. So this is different from distance, because distance is just the magnitude of the displacement, as we saw here. But distance traveled would be the total distance traveled by whatever object it is we're talking about. We're We're going to take a look at an example of all four of these in action in a second and see how they sort of differ. The SI units, or System International units for all these things, are meters. Position, displacement, distance, and distance traveled, these are all measurements of length, and in SI units we measure all of these in meters. And so in general, we're always going to want to convert back to meters when we're doing calculations that deal with distances, right? So we might be given a problem where the problem is stated in terms of centimeters, or stated in terms of kilometers or miles or light years or something. Generally speaking, we're going to want to convert back to meters right away, do the calculation, and then finish the calculation in meters, and then maybe once we have our final answer, if it makes more sense to convert back to some other units, we can do that. But we really want to be using SI units, and the SI units for length are meters, so we really want to be using meters whenever we're doing these calculations involving lengths, to avoid any sort of confusion or making any unnecessary mistakes. Okay, so here I have a little example that we can take a look at. That's going to sort of illustrate the difference between displacement, distance, and distance traveled. Okay. So here I'm going to read the problem. We have Alan, Bob, and Cindy. They're all standing roughly at the same point on a long, straight, narrow path. The path runs east-west, and now each of them walks some different distance, and we're going to talk about what that's sort of going to look like and what these different values would be like at these different points here. Okay, so I'm going to draw this out. One of the best ways to solve problems like this is always to start out by, well, first reading the problem, making sure we understand what's going on, and then drawing ourselves a little bit of a picture. So imagine we have some long, straight road here, and we have our origin here. This is where they all start off at. We can call that x naught. Okay, and then we know that Alan walks 50 meters east and then stops, right? So Alan's going to walk, let's say this is 50 meters. We'll call this XA, and this is equal to 50 meters. Okay, so Alan walks here and stops. Bob walks 40 meters west and then stops. Okay, so if this was 50 meters east, maybe this is going to be 40 meters west. Except that I should write this as negative 40 meters, because we're moving in this direction, which is our negative x direction on our coordinate system here. Okay, so Bob has walked to here, and then Cindy first walks 50 meters east. So Cindy walks 50 meters east, and then walks 90 meters west. So 90 meters west is going to take her back through the origin and all the way over to where Bob is. So Cindy ends up here also. Okay. This is what describes Cindy's walking path here. Okay, so we want to describe the displacement, distance, and distance traveled for all three of these walkers once the walking is done. And I'm just going to erase these lines here so that the notes are nice and clean for you guys. Oops. Okay, so I think the best way to do that is going to be to make a little table here. So let's do that. Let's say Alan, Bob, Cindy, and we want to look at displacement, distance, and distance traveled. So okay, let me finish the little table here. And I'll scroll down to give us a bit of space. Okay, all we need is the chart now. Okay, so displacement, and we want to keep in mind these definitions up here. So displacement is just is just going to be our final position minus our initial position. So we can quickly write all those down for all these walkers. So for Alan, he simply walked 50 meters to the right and stopped. So in the end, his final position, his x final, well, let me write the definition down here. Going to be x final minus x initial, right? This is displacement. That's terrible. Hold on. Okay. And so his final position is 50 meters. His initial position was 0 meters. 50 minus 0 gives us 50 meters. Okay. For Bob, he started off at 0 meters and ended up at minus 40 meters. And so his final position is minus 40 minus 0, which is simply minus 40. Okay? And Cindy ends up at the same position as Bob. It doesn't really matter how she got there. All we're interested in is final position and initial position. She ends up at a final position of minus 40. She started off at an initial position of 0, so she also has a displacement of minus 40 meters. Okay? Now the distance. What is the distance? Well, from above we know that distance is just the absolute value of our displacement. And so that's really simple. We just take the absolute value of all these values here, and we end up again with 50 meters for Alan. Now we have 40 meters for Bob, and also 40 meters for Cindy, right? We're just taking the absolute value of these values from above, and it just gives us the absolute value of the distance from the origin that all three of these walkers are. And now finally, distance traveled. Distance traveled is just the total distance covered in getting to that final position. So for Alan, it's simple. He started off at 0, only walked out to 50 meters and stopped. So his distance traveled is just 50 meters. For Bob, same idea. He only walked 40 meters. He walked 40 meters in the direction of our negative x-axis here, and so his distance traveled is again just 40 meters. But in the case of Cindy, it's a little more complicated. She walked 50 meters in this direction first, and then 90 meters back in this direction. So basically, she walked 50 plus 50 more meters to come back to the origin, and then 40 additional meters, right, this part here, 40 additional meters to get out to where Bob was. And so this is 140 meters. And so I'm going to erase this and just drop the 140 meters in here. Okay? So that's our example that kind of shows us the difference between displacement, distance, and distance traveled. Okay. So in introducing displacement, distance, and distance traveled, we've kind of inadvertently talked about two different quantities here, scalars and vectors. And this is just a very quick introduction to scalars and vectors. We're going to talk more about scalars and vectors as we move into 2D kinematics in the upcoming chapters. But for now, we want to think of a scalar as a quantity that has only a magnitude but no direction. So a good sort of intuitive example of what a scalar might be would be temperature, right? So if you talk about the temperature in a room, it doesn't really have a direction or anything. It just has a magnitude. It's some number of degrees. So in the room where you are now might be, say, 20 degrees or something, right? So scalars only have magnitudes. A vector is a quantity that has a magnitude and a direction. So position and displacement are both vectors. When we talk about something's position, we need to talk about how far it is, but also what direction it's in, right? So if we're talking about it, let's say we're talking in one direction, or we can even look back to our example up here. We can see that if we're looking at where Bob is, how would we describe Bob in relation to our origin here? We would say that he's 50 meters in the positive direction away from the origin, right? So that's the position, and that's we need both of those values to describe it. We need to talk about the distance and the direction. Cindy would be 40 meters in the negative x direction, right? So the quantities that we've just talked about in position and displacement, both of those are vectors. Both of those require magnitude and direction to be able to describe them. The distance and distance traveled, these are scalars. They don't have a direction associated with them. When we ask how far from the origin is Alan, we say 50 meters. It doesn't give us any information about direction, but it is the distance from the origin that Alan is, right? How far from the origin, or what's Bob's distance from the origin would be one way to think about it. And Bob's distance from the origin, well, it's just 40 meters, right? Like we had here. And I probably shouldn't mess up the notes here. Let me fix that up really quickly here. Okay, so again, just to reiterate here, position and displacement, those are vector quantities. Distance and distance traveled are scalars. And this will become sort of more intuitive and more useful as we move on, but just keep that in mind for now. Okay, so some of the other quantities we're going to need to talk about in discussing kinematic systems are time, velocity, and speed. So let's take a look at those now. So time, the SI units for time is seconds, and so we're going to try to, as often as possible, convert all of our times back into seconds when we're doing calculations. And time is just described as the quantity over whose interval change occurs, okay? And so, again, our change in time, our delta t here, is defined as follows. So we have our final time minus whatever the initial time that we started looking at the problem was. But we have control, generally speaking, of when we start the stopwatch in our experiments or in whatever calculations we're doing. So in general, we're going to choose to set this t0 to 0, and if we do that, we can see that from what I have written down here, we can see that the change in time is just really equal to the final time if t0 is 0, right? If t0 goes to 0, this means that delta t goes to tf, and then just to simplify the notation, we just end up calling this t. Okay, so generally speaking, when we're writing down our kinematic equations later, we're going to see that we end up with our equations written in terms of t and not delta t, but that's because we've set the initial time to 0, and we're just counting our final time as our time. Okay, and this is all laid out in this paragraph below here, so I'm not gonna keep these notes here, which is just kind of messing up the PDF here. But that's what's described here, and it's just good to keep in mind that when we're talking about time, we should always be thinking about delta t, but we often just write t because we've set t naught to 0. Okay. Okay, so now that we have some idea of distance and displacement and things that we think about as lengths and things that we think about as times, we can now describe something that involves both of those. So we're going to start by looking at velocity here, and velocity is defined as a displacement over a change in time. So when we talk about, well, we can either talk about an average velocity or we can talk about an instantaneous velocity. And the SI units for both of these are going to be meters per second, right? So we saw the SI units for a displacement is meters, the SI units for time is seconds, and so we end up with meters per second for our velocities. Okay. So again, velocity is a vector because velocity is described by a vector over a scalar. So again, velocity is going to be a vector, which means that it's going to have a magnitude and a direction. And we have our definition of average velocity down here. Average velocity is always going to have this symbol v with a bar over top, and the bar is just indicating that that's our average velocity. All average quantities will end up with this bar over top. And so as we discussed above, average velocity is going to be defined by displacement, which we saw before, over a change in time. But since we're setting t naught to 0, we often just see it in this form here, where it's just delta x over t. And that just means this, what we see over here. So it's just going to be the final position minus the initial position over the time it took to go that distance. Okay. And I'm going to erase this also. So that's average velocity. We can also talk about instantaneous velocity. Now, instantaneous velocity for an object is the velocity at whatever instant in time we're looking at that object. So to have a really flexible definition for instantaneous velocity, we need to use some calculus, and basically what's going to end up happening is our delta x is just going to go to a dx, and our delta t, our change in time, is just going to go to an infinitesimal change in time, a dt. And that's going to mean that our velocity goes to an instantaneous velocity. Now, we're not going to be using calculus, and so we're not going to use this equation at all. But we're going to find that in many cases, we're able to get an instantaneous velocity through other means, and that's sort of what we're going to be looking at in the next video here. I'm going to erase these again to not mess up the notes, but just keep in mind, don't be concerned that you see some calculus here. We're not going to be using this equation. It's just good to know that there is a way, a sort of more flexible way to get these instantaneous velocities if we would need them. Okay, so we've talked about velocity, which was a vector, right? And it's described by this change in displacement over a change in time. We can now talk about speed also, and speed, like velocity, comes in sort of two varieties, an average speed or an instantaneous speed. Again, the SI units for speed are going to be meters per second, but unlike velocity, speed is a scalar. Okay, and so speed doesn't really have or doesn't have a direction associated with it. It only has a magnitude. Okay, and here are our definitions for the two types of speed that we're going to be talking about. So average speed is just defined as the distance traveled over time. So if we think back to that problem that we looked at a moment ago, in the case of Cindy, well, she traveled sort of 50 plus 90 meters, so 140 meters, right? So if we were interested in her average speed, we would simply enter in that 140 meters in this case over here, and we would need to know how much time it took her to make that journey, and we would enter the time in there, and we would be able to find her average speed over the full journey that she took there. Okay. Instantaneous speed is really just the magnitude of the instantaneous velocity. So if we were able to find the instantaneous velocity in some system, and as we talked about here, we're going to find other ways to do it, but one way to do it would be to use calculus here. We could then easily extract the instantaneous speed just by taking the absolute value of that quantity. And what are we doing when we're taking the absolute value? Well, the velocity, the instantaneous velocity, is a vector. When we take the absolute value, and if we're talking about a problem in one dimension, we're pulling off the sign off that value, right? So it could either be negative or positive depending on which direction along the x-axis it's pointing. When we take the absolute value, we're peeling off that information about the direction, and we're only left with a magnitude. And that's really what we want here. Our speed is a scalar. It only has information about the magnitude, so we take our vector quantity, peel off that information, and we're left only with information about the magnitude. Okay. Let's take a look at an example here of the difference between velocity and speed. Okay, and so we're going to be talking about driving a car, I believe, to the airport along a long straight road here, right? Okay, so let's take a look. Okay, so the distance from our home to the airport is 100 kilometers. On the way there, we drive 100 kilometers per hour. And as soon as we get there, we turn around and we drive back at 50 kilometers per hour. We would like to be able to say something about the instantaneous velocity, the instantaneous speed, the average velocity, and the average speed at different points on the trip. Okay, so again, let's start off by drawing ourselves a picture here. So let's call this our house. Call this the x-axis. So this is our house. This is going to be at the origin. We'll call this x not equals 0. This is our origin. And this is the airport over here. And that's going to be at, call that XA for airport. It's going to be 100 kilometers. Okay. And so what are we doing here? We're driving at 100 kilometers an hour consistently in this direction. And then on the way back, we're driving 50 kilometers per hour. Okay. And so what can we say about the velocity, either instantaneous or average, and the speeds, either instantaneous velocity over the trip? Okay, so let's take a look at what our instantaneous velocity would be at any point on our trip from the house to the airport, right? So at any point as we're going from the house to the airport. Well, that's pretty simple, right? We have our velocity, or maybe I'll clean this up a little bit here. We'll divide this up into a few different categories. So let's say at any point on the trip to the airport. Okay, so on the way to the airport, at any point on the way to the airport, our instantaneous velocity is going to be equal to plus 100 kilometers per hour, right? Because at any point on the way there, we're moving in the positive direction, so I've stressed that by including this plus sign here. And so we're moving at 100 kilometers per hour in the direction of the airport, right? And on the way back from the airport, at any point on the way back from the airport, our velocity is going to be equal to minus 50 kilometers per hour, right? Because no matter what point on the way back we're always traveling 50 kilometers per hour, right? Okay. What our speeds, our instantaneous speeds, going to be along both of these different directions? So our speed at any point going to the airport, well, that's just the absolute value of the instantaneous velocity, right? And so that's just going to be 100 kilometers per hour. And similarly, on the way back, it's just going to be the absolute value of the instantaneous velocity again, and so that's just going to be 50 kilometers per hour. Right, so in taking the absolute value, we're just dropping this negative sign here. Okay, now what is our average velocity for the full trip? Okay, so for the full trip, what is our average velocity? Okay, well, let's think back to our definition of average velocity. We know the definition of average velocity is just going to be our displacement over the time it took us to make the trip, right? And so what is our displacement? Well, our displacement is just our final position minus our initial position over the time it took. Well, what's our final position? Our final position is just back at home, right? So that's 0. And our initial position was also 0. we can put the time in here, but we can already see this is going to end up being 0 because our numerator is going to be 0. It took us 3 hours to make the trip, but so we end up with an average velocity of 0 kilometers per hour, right? And that's because we have no displacement over the full trip, right? So we could talk about a number of different points here, but if we're talking about the full trip, we end up right back where we started. There is no displacement, and so there is no average velocity. What is the average speed, though? And let's quickly look up here. Let's remind ourselves that the average speed is given by the distance traveled divided by the time it took to make that trip. So we have distance traveled over the time it took to make that trip. Well, we just saw that the trip took 3 hours. And how far did we go in that 3 hours? Well, we went 100 kilometers in one direction, and again, same amount, 100 kilometers back. So that's 300 kilometers. And so our average speed over the trip was, confused myself there. It's actually 200 kilometers, right? Because it's 100 kilometers in one direction and another 100 coming back. Sorry about that. And so we end up with 200 divided by 3. That's going to give us something like 66.6 kilometers per hour, or I guess this would work. Okay. And so this is just a quick sort of demonstration of the difference between velocity and speed, both instantaneous and average. Okay. We have one more quantity that we need to define here before we move on, and this is going to be average acceleration. So the average acceleration is defined as the average rate of change of the velocity over some given time period, right? And so we see the definition here written in the form of an equation. We have our average acceleration, again with a bar over top, and it ends up boiling down to our final velocity minus our initial velocity divided by the time over which we're accelerating. Okay. The SI units for acceleration are going to be meters per second, or meters per second squared. And this is because we had meters per second in our velocity, and we're dividing by another units of seconds, and so we end up with meters per second. Okay. There's a few things that we should probably note here. First, that deceleration is not the same as negative acceleration. Okay. When we move beyond one-dimensional problems, these things don't generally have to be the same thing. In general, deceleration is acceleration directed in the opposite direction of the velocity or of the motion, where negative acceleration is coordinate dependent. It'll depend on what coordinate system you have imposed in your problem, and we'll sort of see this playing out as we look at future examples here. Okay, so we can also define instantaneous acceleration, but again, to get a really flexible definition of this, we kind of need calculus. We're going to find that for the purposes that we're going to be using acceleration for, and the types of problems that we're going to do, as long as we're careful about what intervals over which we're measuring acceleration, we're not going to need to worry about any of this. And again, we're just not going to be using any calculus in this course at all, so don't worry about this too much, but just be aware that there is a way to do this sort of more rigorously with calculus. Okay, and I don't have it on the slide yet, but I do have a little sort of thought experiment that we can do here involving acceleration and velocity that kind of gives us a feel for how these quantities might interact. And this is actually taken directly out of the text from figure 2.14. And so we're going to have 4 cars here. I'm going to draw 4 terrible looking cars. Okay, so these are our 4 cars. Next to them, I'm going to put arrows which are going to indicate the velocity. So this is the direction that the car is moving, and then there's some acceleration that the car is experiencing. And in this case, they're both going to be in that direction. And in each case, they're going to have different configurations here. So let me draw those in. Okay, so if we look at the first car, this one up here, and we think to ourselves, well, what's really happening here? What would we see? What would we see if we saw this car and it had a velocity pointing in this direction and acceleration acting on it, or it's experiencing this acceleration, I should say? Well, what we would see is that the car is moving right, and it's speeding up, because it's accelerating in the same direction as its velocity, right? In this second case, maybe take a second to guess what you think would be happening here before I write it down. But what we would see here is the car is moving right, and it's slowing down. Right? It's slowing down because our acceleration vector is pointing in the opposite direction of our velocity. Maybe take another second to think about what these other 2 cars might be doing. But I think we can see that in this case we have a car moving left and slowing down again. Right, so it's moving left because the velocity vector is pointing left, but it's slowing down in its movement to the left because the acceleration vector is countering that velocity vector, right? And finally, in this case, we have the car moving left and speeding up. And again, because the velocity vector is pointing left and the acceleration is also pointing left, it started off with some velocity going to the left, and the acceleration is increasing that velocity. So we're seeing it move more and more quickly off to the left. Okay, so one final example here for this video, and then we'll move on. In this example, we're going to be taking a look at average acceleration. So we're going to take a look at a racehorse coming out of the gates from rest to a velocity of 15 meters per second, pointing down the track. And it's doing this in 1.8 seconds. So we want to find what the racehorse's average acceleration is, right? Okay, so let's quickly just draw a little picture here. We have our racehorse. Okay. It's coming out of the gates here. We can set the gates as our origin. It starts off with some initial velocity, but the initial velocity is 0, right? Because it starts off from rest coming out of the gates. And then at some point, the horse has moved forward, and at some point in the future, at a time of 1.8 seconds, it has a velocity final equal to 15 meters per second. Okay, and we want to find what the average acceleration is. Well, to start off, we need our definition of average acceleration, and we can grab that from here. So that's just our final velocity minus our initial velocity over the time it took. Okay, so that's velocity final minus velocity initial over the time it took to make that change in velocity. And this is basically the equation that we're going to want to work with, so I'm just going to box that off here. And now we're going to substitute in values. So let's write down the equation again. Average acceleration is going to be equal to final velocity. Well, final velocity is 15 meters per second, minus initial velocity. Well, initial velocity was 0. And it took how long to undergo that change in velocity? 1.8 seconds. Okay? And so we end up with 15 over 1.8. And I think I've done that over here. Yes, that works out to be 8.33. Oops. And so we want to write our final answer with units on it. And so that's going to give us 8.33 meters per second squared. Okay? Box the final answer. And that's just a quick example of how we would use average acceleration. Okay, and that's going to conclude our first video on algebraic kinematics in one dimension for this series.